Good afternoon, everyone. So this is my next lecture, lecture number 20, based on MOSFET. And in the last lecture, we have discussed about metal oxide semiconductor field effect transistor, their types and how they can be constructed on the basis of their characteristics like N-type or P-type MOSFET, or different type of MOSFETs like enhancement or depletion type of MOSFET. So in this lecture, we are going to see how the depletion or enhancement type of MOSFET can be constructed using this MOSFET characteristics, and we see what are the characteristics of MOSFET in the input and the output characteristic and their data sheets for industrial applications. So in the last lecture we have discussed about N-channel depletion MOSFET. So in this lecture we are going to start with the P-channel depletion type of MOSFET. So as the word defined itself, that is depletion. Depletion means the depletion of the channel between the source and the drain. So we have here this source and this drain. So what we are having, P plus type of, which is heavily doped drain, that is P plus doped, that is heavily, because it's P plus, so it is heavily doped drain. Similarly, we have heavily doped source. Heavily doped source. So whenever we assign positive ion to the P type or N type, it is heavily doped, we know it. So we have source and the drain. In between the source and the drain there is a gate. So firstly we have some conditions like VGS, which is gate to source voltage, which we are applying at the gate. It must be greater than V threshold. So this is the mandatory condition for having the MOSFET to work in depletion mode. So here we are using N type of substrate. So as we know that we require three particular things, like first one is the substrate for constructing MOSFET. Second is the SiO2 layer, which is the oxide layer, and the third one is the metal layer. So these three prerequisite is important for having a construction of the MOSFET. So we have N type of substrate, P plus type of heavily doped source, and the P plus type of heavily doped drain. In between the source and the drain we have this channel, particular channel, which is already constructed. So P channel is already constructed between the source and the drain. So what we are seeing here, that whenever you apply the voltage, that is VGS is greater than V threshold, the negative is connected with the gate and the positive is connected with the body. So whenever you are applying negative voltage to the gate, obviously the N type having more number of electrons. So this substrate has more number of electrons because it's N type. So it has more number of electrons. If it is P type, more number of holes are there. So as this is N type, more number of electrons are there, and we are applying negative charge, negative supply to the gate. So obviously it will repel the N type of charge carriers. So whatever the, or you can say that it will attract the P type of channel, the positive channel between the P plus source and the P plus drain. So obviously the channel will get now depleted of the between the source and the drain. So firstly we have to see that what will be the substrate we are using for the MOSFET. Then we have to see what type of source and the drain we are using for the MOSFET, and then we have to see what type of biasing you are applying at the gate. So if it is negative biasing applied to the gate, obviously it will attract all the holes towards the gate and the channel will get depleted of the number of holes, because here initially the holes are high. So whenever you apply the negative voltage, holes becomes attracted towards the negative ions, and this particular region will get depleted of the holes, which is a carrier. So if it is P type substrate, suppose this is P type substrate, then there will be N plus and N plus type of source and drain, and the channel is N type. So in that case you have to apply the positive voltage to the gate so that the electrons get attracted towards the positive voltage and the channels will get depleted of the negative ions. So this is the overall working of the p channel depletion type of MOSFET. So as we have discussed in the last lecture, that is enhancement and depletion type of MOSFET. So in what if you are taking, see the difference between both these type of MOSFET. The enhancement type of MOSFET has the channel is not present in the case of the enhancement type of MOSFET, but in the depletion type of MOSFET, the channel is initially present. You have to apply the proper biasing to the channel, to the gate, so that the channel get depleted of the charge carriers. So if we see, look at the characteristic of the p type of channel depletion type of MOSFET. So we have here the output characteristic between VDS and ID, the input characteristic between VGS and ID. So VGS is your gate source voltage. This is your gate source voltage, which is applying at the gate source, between the gate and the source, and ID is your drain current, is in milliampere. So in the first figure, A figure, you can see that we have same the gate and the substrate. Substrate is of N type, the P plus type of source and the drain, and the P channel is created between the source and the drain. We are applying the positive voltage. Whenever you apply the positive voltage, the holes will get repelled from the positive voltage, and what will be happen, that these holes will move towards the N type of substrate, and obviously there will be the depletion of the channel between the source and the drain, and the current will flow from the drain, that is your ID current. So as we increase the voltage VGS up to threshold voltage, it will not work, but after the threshold voltage it will work, and MOSFET will work, and the current will keeps on increasing. So in the case, if you see the difference between the N type of depletion type of MOSFET and P type of depletion type of MOSFET, the characteristics are similar but in a reverse type. So when you increase the voltage VGS from 1 to 2, 3, 4, 5 and 6, at a particular value 6, you can see that there will be a 0 ID current. So at 0 means that when your VGS is equivalent to 0, in this case ID is equivalent to IDSS. So whenever the voltage you are taking, the pinch gate source voltage is 0, the current is higher, and when you increase the gate source voltage in the P type of depletion type of MOSFET, the current keeps on decreasing, and in the negative direction it's opposite. Whenever you increase the voltage in the negative direction, the current keeps on increasing, just reverse from the N type of depletion type of MOSFET. Similarly, in the output characteristic, we have VDS and ID, and the constants are here VGS, which we are applying at the gate and the source. So at 0 volt, the current will keeps on increasing, but as you increase the voltage, the current keeps on decreasing. So here, this is the main difference between P type and N type of depletion type of MOSFET. In N type, whenever you increase the VGS, the current will keeps on increasing, just opposite of these graphs. So here we are at VGS is equivalent to 0, we have some current, and when VGS you are increasing, like VGS at plus 1 volt, plus 2 volt and so on, you are seeing that the current ID current will keeps on decreasing. So in this case, the ID current will keeps on decreasing. So as you increase the VGS, the current will keeps on decreasing. Similarly, in the reverse direction, as you increase the negative voltage, because if you are applying negative voltage here, the holes will get attracted towards the negative voltage. Obviously, the current will keeps on increasing because the channel will get depleted from the charge carriers. So as you increase the negative voltage from VGS is equivalent to minus 1 volt to minus 2 volt to minus 3 volt and so on, the current will keeps on increasing. So in N type depletion type, what will happen? VGS is equivalent to 0 volt, there is some current, suppose IDSS, VGS is equivalent to plus 1, plus 2 and so on volt, ID will be greater than IDSS. But in P type, this is your first case. The second is P type depletion type of MOSFET. When VGS is equivalent to 0 volt, then there will be current some IDSS, but when you increase VGS is equivalent to +1, +2 and so on, the ID is less than IDSS, just opposite of the N type of depletion type of MOSFET. So next we have the MOSFET, which is enhancement type of MOSFET, and it is also known as E-MOSFET. So this schematic symbol for the N channel and P channel E-MOSFET are shown in the given figure, which is just below, and we have the current direction, because for the N channel the current is inward and for the P channel the current is outward. So here we have to note down this also, that the current direction is from positive to negative side. So whenever there is N channel, the current is inward, and whenever there is a P channel, the current is at outward. We have the gates similarly, which is similar to the base. We have source, which is similar to the drain, and we have drain, which is similar to the collector. Similarly, in the P channel, we have the outward current direction. Same, we have source, gate, drain. So here it is source, gate, drain. So we, in the construction point of view, if you see the construction of the enhancement type of MOSFET, we have P type of substrate, which is obviously a P type. How it is created P type? Whenever you import trivalent impurities. Similarly, we have N type of substrate here and N type of source and the drain here. So this is your source N type of, and this is your drain N type of. So normally it is N plus because it is heavily doped. So we have a channel which is basically N type of channel. So this is your N type channel in between the source and the drain. So you apply here voltage at the gate and the source. Between the gate and the source, we just apply some voltage here. So suppose we are applying a negative voltage. So obviously if you are applying the negative voltage, it will repel all the electrons at the channel, and the channels will get depleted. So here we have to enhance the channel. So what we will do, we will apply a positive voltage here. So if you apply a positive voltage at the gate, between the gate and the source, the electrons will get attracted towards the positive voltage, and what will happen, there will be a layer of the N type of electrons in between the N channel. So what will happen, obviously whenever you apply a voltage, you have to see what type of substrate is in the MOSFET, and what type of source and the drain is there. So accordingly there will be a depletion or an enhancement type of MOSFET to be formed. So this is the next figure, which is basically the enlarged version of the last figure, which shows the N channel enhancement type of MOSFET construction. So we have the P type of substrate here, N type N doped region here, which is a source, N doped region here, which is a drain. There is no channel present between the source and the drain. So we have to take care of this point, that at enhancement type of MOSFET, so whenever you use enhancement type, there is no channel initially. But when you are using depletion type of MOSFET, there is channel present initially. So in the enhancement type, there is no channel. So that's why I have shown here that there is no channel between the source and the drain. But we have to form a N type of channel here. So what we have to do, we have to attract the negative ions from the P type. So what we are going to do, we apply the positive voltage here at the gate. So whenever you apply the positive voltage here at the gate, obviously the number of electrons in the P type of substrate, because it has both the number of, there will be some electrons and there will be some holes. So it consists of holes also and electrons also. So if we want to form the N type of channel, we have to apply a positive voltage here. Then this positive voltage will attract all the negative ions from the, all the negative carriers from the P type of substrate, and it will form a layer of the channel in between the source and the drain. So by this way we can create the N type of N channel enhancement type of MOSFET. Obviously there will be metallic contact at the source and the drain, so that there will be no discharge of electrons or the carriers from these sides. At the gate also we have a metallic contact. As we have discussed already in the last lecture, the metallic contacts are made up of aluminium. So basically we have a SiO2 layer, on the top of that there will be a metallic contact which is of aluminium. So next we can see from the theory itself also, and we have already discussed about enhancement type of MOSFET construction. So basically these figures shows the construction of an N-channel E-MOSFET. The main difference between the construction of depletion type and enhancement type MOSFET substrate extend to all the way to the silicon dioxide, and no channels are doped between the source and the drain. So obviously in the enhancement type of MOSFET there will be no channel between the source and the drain, as in the case of the depletion type of MOSFET. So this is the first point which we have to see. Second point, two highly doped N regions are diffused in type of substrate, because when we are using a substrate it should be of a lightly doped, but the source and the drain should be of heavily doped. That may have an additional terminal connection called as substrate. The source and the drain are taken out through the metallic contacts to the N type of doped regions. So these N doped regions are not connected via an N channel without an external voltage. Whenever you apply the voltage, only in that case the source and the drain will be connected through a channel. Before that there will be no channel present in the case of the enhancement type of MOSFET. Similarly, there will be third point, that is the gate connects to the P type of substrate via thin insulating layer of SiO2. So below the gate there will be an SiO2, that silicon dioxide layer, and channels are electrically induced in these MOSFETs whenever a positive gate source applied, VGS is applied to it. So whenever you apply VGS, obviously it should be that VGS should be greater than or equivalent to threshold voltage or VT voltage, that is your threshold voltage. So whenever it is greater than VT or the threshold voltage, only in that case the channel will be effectively formed or induced in between these source and the drain. So next we have N-channel enhancement MOSFET operation. So these MOSFET operates, this basically theory gives you an idea about how these MOSFETs will operate in the enhancement mode and in the depletion mode. So it operates with large positive gate voltage only when drain is applied with positive voltage with respect to the source and no potential is applied to the gate. A very small drain current that will flow through the MOSFET, and which is basically called as leakage current or the evanescent current. So the E-MOSFET does not conduct whenever the VGS is VGS having the value 0. This is a region, it is normally called as off MOSFET. So whenever there is no VGS or the gate source voltage is applied, that particular at that time it is called as enhancement type MOSFET is called as off MOSFET. Second point, when the gate is made positive with respect to the source and the substrate, that is negative, that is minority charge carriers within the substrate are attracted towards the positive gate and it get accumulated close to the surface of the substrate. So as the gate voltage is increased, more and more number of electrons get attracted towards the gate, and these electrons will obviously form a channel between the N type of source and the drain. So when this occurs, a channel is induced by forming what is termed as inversion layer. So obviously this is called as inversion layer, which is the N type of layer which is formed between the source and the drain. So now a drain current start flowing. So in that case, whenever the channel is formed, only in that case the drain current will start flowing. So ID will obviously increase only whenever the channel is formed in the case of the enhancement type of MOSFET. Similarly, the ID is only start flowing whenever there will be depletion of the channel in between the source and the drain in the case of the depletion type of MOSFET. So the conditions are I think understood by you, that is whenever the depletion type of MOSFET is there, channel has to be depleted, only in that case the current will increase. Whenever you have to enhance the channel, only in that case the current will going to increase or the ID will get increased to a particular value. For that case, we have a necessary condition that VGS should be greater than threshold voltage. So next we have N-channel enhancement MOSFET operation. So at a particular value of VGS, there is measurable current between the drain and the source, and this value of VGS is called as threshold voltage, which is called as VT. So for any voltage below VT, there is no channel. So whenever there is, obviously whenever VGS is less than VT, in that case there will be no channel. So no channel is formed. Okay, so we have here transfer characteristic for N channel enhancement MOSFET. So here VGS is increased for a particular value, after that VT, that is 3, 4, 5, 6, 7, 8. So before VGS is less than VT, there will be no drain current, that is ID is equivalent to 0. As you increase VGS above 3, 4, 5, 6, 7, 8, at these values we have different values of the drain current. So the current IDSS at VGS is less than equivalent to 0 is very small. When the VGS is made positive, the drain current ID keeps on increasing slowly at first, and then it will be much more rapidly increased above the threshold voltage. So the first requirement is obviously the gate source voltage must be greater than or equivalent to threshold voltage. Only in that case the drain current will keeps on increasing. So initially it will be slow, and after that it will increase rapidly. So the drain current attains some defined values, say something approximately equivalent to 10 microampere. The equation for the transfer characteristic is given by ID is equivalent to K VGS minus VT ka whole square. Similarly, from this equation we can find out the value of the constant, that is K, because ID is increasing not a linear proportion, but at a initially it is very small, but after that it will rise rapidly. So it's a ID is initially ID is proportional to VGS minus VT ka square, or you can write ID is equivalent to K VGS minus VT ka square, or from here we can easily calculate the value of the K, which is IDS or ID on upon VGS on minus VT ka whole square. So by this value we can find out the constant term K. So here we have E MOSFET transfer characteristic and parameters. So the E MOSFET for all practical purposes does not conduct until VGS reaches the threshold voltage. ID when conducting can be determined by the formula, that is we have already discussed, that is that ID is equivalent to K into VGS minus VT whole square. So or we can write K is equivalent to ID on divided by VGS minus VGS threshold to the power square. Similarly, from here we can calculate ID is equivalent to K VGS minus VTH whole square. So by these equations we can plot the graph between VGS and ID. If you plot the graph between VGS and ID, we have a linear curve. Similarly, for the N channel and for the P channels, for the N channel it is exponentially increasing in the positive direction, and similarly for the P channel it is exponentially increasing in the negative quadrant. So it is in the positive quadrant, and similarly it is in the negative quadrant. So as we have already discussed, the P channel characteristic are similar to N channel, but it is in reverse direction. So it is in positive and it is in reverse direction, and obviously the same thing is here, that we have to increase the VGS value after that the threshold value. Only in that case the current will keeps on increasing in both the cases. So an N channel device requires a positive gate to source voltage, and a P channel device requires a negative gate to source voltage. So whenever there will be N channel, we have to form a N channel. That's why we have to see whether the voltage applied at the gate and the source is the positive voltage. Whenever we have to form a P type of channel, we have to form a layer of holes. Then we have to apply a negative biasing at the gate and the source to make sure that there will be more number of holes in the channel between the source and the drain. So E MOSFET general transfer characteristic curve shows in the left side will give you an idea or about the N channel type of enhancement MOSFET and the P type of channel enhancement MOSFET. So we have P channel enhancement mode MOSFET. So P channel enhancement mode MOSFET is similar to the N channel, except that the voltage polarities and the current directions are reversed. So both are same, only the directions has been changed. So here we have in the negative quadrant, that is -1, -2, -3, -4, -5 and -6. So at VGS is greater than VT at a particular threshold, this threshold value. Before this the current is 0, and after this the current keeps on increasing. Similarly, in this graph, in the output characteristic between VDS and ID, we have the at a constant value of VGS, we see that the current will keeps on increasing in the negative direction. So whenever you apply the voltage in a negative way, like -3 volt, -4 volt, -5 and -6, the currents keeps on increasing. So this is the E MOSFET symbol. symbol is same for both the depletion and the enhancement type of MOSFET. In the depletion type of MOSFET, we show the channel is present. In the enhancement type of MOSFET, we don't show the channel is present. So for the N channel, it is the inward direction current, and for the P channel, it is the outward direction current. So we have to see that for the N channel, this is shown here. That is the symbol for the N channel, the inward direction current. So summary table for JFET, D MOSFET and E MOSFET is shown here. So for the JFET, we have at particular gate current Ig is equivalent to 0 and Id is equivalent to Is. So in that case, Id is equivalent to, the equation is Id is equivalent to IDSS 1 minus VGS upon Vp whole square. Similarly, for the curve, output characteristic curve, we have VGS and Id. Input characteristic curve, we have VGS and Id, and we have a value of at 0 voltage it is IDSS, and at a particular negative voltage, that is called as pinch off voltage, 0.3 Vp and Vp by 2 or Vp. What will happen? This is all negative. What will happen? The current will keeps on decaying. So at 0 it is IDSS, at minus 0.3 Vp it is IDSS by 2, at minus Vp by 2 it is, or 0.5 Vp it is IDSS is by 4, and for Vp is equal, for VGS is equivalent to minus Vp, it is again 0. So the current will keeps on decreasing. Similarly, for the D MOSFET, we have seen that the equation is Id is equivalent to IDSS 1 minus VGS upon Vp ka square. And in this case also, because it is a depletion type of MOSFET, we don't have the channel present. We have the channel present. We have to get depleted the channel between the source and the drain. The current curve will shows here that as you increase the VGS, the ID current, the diode current will keeps on increasing. Similarly, for the E MOSFET, we have seen this equation, that is for finding out the value of the K. We have to see what will be the value of the VGS and VGS threshold. So until unless VGS is greater than VGS threshold, we cannot find out what will be the value of the drain current. So thank you so much. So in the next lecture, we are going to see about the different semiconductor devices like LEDs and laser. We get into detail of these devices because these devices are nowadays useful in very multiple industrial applications, and these devices along with the MOSFET and the BJT can be used in various applications. So thank you so much.